Okay, so in the last video we talked about the concept of the electric field, and we talked about how the electric field is defined. Basically, the way the electric field is defined at every point in space is if you were, hypothetically speaking, to put a test charge at that point in space, and you measure the electric force that acts on that test charge, and divide by the magnitude of the charge, then that gives you the electric field value at that point in space. Remember that electric field has a symbol of a capital E. It is a vector, and it has newtons per coulomb as the unit. Okay, so what we're going to do now is we're going to basically derive an equation that allows us to calculate the electric field strength due to a point charge. Now, typically speaking, electric fields are actually very difficult to calculate in practice because in real-life situations you have bajillions of charges, and in the best-case scenario you need some type of calculus to be able to find the electric field due to a bajillion different point charges, and usually it involves some type of integral. And in the worst-case scenario, you have a situation that you basically have to do with like a computer program to figure out what the electric field is due to a really complicated distribution of charge. And so what we're going to focus on is basically finding an equation that allows us to calculate the electric field strength due to a single point charge at a distance r. Because remember, it is charged particles that actually give rise to electric field, and so every charged particle has its own electric field. And so we're going to derive an equation for that, and the derivation looks something like this. Okay, so imagine you have some charge out in space, and let's say that charge is Q, big Q. Okay, this is the charge which is going to create our electric field. Okay, at some distance from big Q in space, let's say that distance is r, we have an area of space which obviously has an electric field at that point, and that electric field is created because of big Q. Now, hypothetically speaking, let's say I go to this point in space, I take a test charge out of my pocket, and let's say that test charge has a value of little q, and if I were to measure the electric force at that point in space, and divide by the value of my test charge, which is little q, that by definition would be the electric field strength at that location in space. Okay, that is the definition of the electric field. However, I actually know how to calculate the electric force between big Q and little q. Okay, because that's one of the first things we talked about in this unit, is how to find the electric force between 2 point charges, and that is using Coulomb's law. And so remember, Coulomb's law allows us to calculate the electric force between 2 charges. That would be K times Q1 times Q2 divided by the distance between them squared. Now in this case, we're going to call Q1 big Q, and we're going to call Q2 little q, and the distance between the two we still call r. Okay, and so this is Coulomb's law. This is the electric force between those 2 charges, which means that the electric field strength at this point in space must be equal to this equation divided by little q. And so if we take this equation that comes from Coulomb's law, that's K big Q little q divided by r squared, and then divide by little q, we arrive at an equation that allows us to calculate the electric field strength at this point in space that is caused just by the existence of big Q alone. And this equation looks something like this. That is K times big Q divided by r squared. This is the equation that allows you to calculate the electric field strength due to a single point charge, big Q. Okay, so if you know the size of your charge and you know the distance away from your charge, you can use this equation to calculate the electric field strength at that point in space. Okay, now of course the issue is that in real life you have bajillions of charges, and so this equation only works for one single point charge. And so again, if you or to actually do this in practice, either you would have to do like calculus and you would have to do an integral to add up, the electric field strength due to each individual point charge, or you would have to write a computer program to do something like that for you. Okay, but this equation allows us to calculate the electric field strength due to a single point charge. Don't confuse this with the definition of the electric field, which is this thing up here. Okay, this is how the electric field is defined at every single point in space. This is just the electric field strength due to a single point charge. They're both equations for E, but they have different connotations. Okay, this equation only works for a single point charge, whereas this equation is literally the definition of electric field strength. Okay, so pause there and make sure you understand how that derivation works, and make sure you have this equation in your notes. Okay, so moving on. Okay, I think this slide right here basically just goes through the derivation that we just went through. I think that's the exact same thing. Okay, so example 4. It says, calculate the strength of the electric field 0.4 meters away from a point charge of magnitude 20 microcoulomb. By the way, one of the interesting things about this equation is notice that in the problem it doesn't specify which direction we have to go away from the charge. And it doesn't matter because the electric field has a spherical symmetry, meaning that the strength of the electric field due to a point charge is the same 0.4 meters away regardless of the direction that you travel in. Okay, and so it's independent of the direction that you travel away from the point charge. All that matters is the distance. Of course, the direction of the electric field would be different. The direction of the electric field, I talked about this in the last video, but remember the direction that the electric field points in is the direction that a positive charge would feel a force. And so if you imagine a positive point charge, the electric field would be going away from it in all directions. I'm simply saying that the magnitude of the electric field would be the same in all directions. Obviously, the direction would be different depending on where you are. Okay, but in any case, to calculate the electric field strength, that's just going to be Q divided by R squared. So we have 9 times 10 to the 9. Q, in this case, is 20 microcoulomb. Keep in mind, again, we're not talking about electric force here. We're not talking about the force between two charged particles. We're talking about the electric field that is created by a single charged particle. So if I go 0.4 meters away from this 20 microcoulomb charge, does that mean that there is an electric force there? No. Okay. All it means is that if I did put a positive charge at that point in space, that positive charge would feel a force. Okay, so I have KQ divided by R squared, so R in this case is 0.4 meters. And so I go to my calculator and I type this in, and I should get the answer that they give you on the paper, but let me just confirm that. Okay, so I'm just typing into my calculator 9 times 10 to the power 9 times 20 times 10 to the negative 6, and then I'm going to divide by 0.4 squared, and I get a very large number, which does appear to be consistent with this. It's actually 1.13, it looks like, times 10 to the 6 newtons per coulomb. And which is actually a pretty big electric field value. Actually, it's in the millions of newtons per coulomb. And we'll talk a little bit more about this later on, but it is a fact, basically, that if you get a strong enough electric field, then you can create sparks, and we'll talk more about that later. But that's kind of has to do with the physics of how like lightning works and stuff like that. Basically, the idea is if you get like a strong enough electric field, you can create sparks, whether that's like in a thunderstorm or even if you've ever like rubbed your feet on the carpet and you reach out to touch the doorknob, you see a little spark there. What happens is in the space between your finger and the doorknob, the strength of the electric field gets so big it can actually cause sparks to fly. And we'll talk more about how that happens later. It's kind of an interesting type of thing. But in any case, that's the answer to example 4. Okay, so pause there if you need to look at that some more. Okay, example 5. This type of question is starting to be more along the lines of the type of question you might see on the IB exam, although typically they don't ask you to do the actual calculations. A lot of the time they'll ask you this type of question in a more qualitative way that we'll see in the next example. Okay, but you should definitely be able to do this type of calculation. So example 5 says 2 point charges are placed on a line as shown to the right. Calculate the magnitude and direction of the electric field at x. Now, a couple things before we start. It's really important that you understand there is not a charged particle at x. X is completely empty space. Okay, don't confuse the idea of the electric force, which acts between two charges, and the electric field, which can be created by a single charge by itself. There is some electric field value at point x, because that's the nature of a field. At every point in space in the universe, there's a single electric field value. That does not mean that there's a charge at x. That does not mean any force is acting at point x. Point x could be completely empty for all I know. But there's still an electric field value at that point in space, and that's what we're going to calculate now. Okay, now notice that we have 2 point charges. Okay, and the picture is actually kind of incomplete. So I'm actually going to say that this distance is 1 meter. In other words, you can see this kind of set up like a number line. This charge is at -1, this charge is at 0. Let's say the star position is at 1 meter. Okay, so each of these individual charges creates its own electric field at point x. And so the way we're going to do this type of calculation is we're going to find the electric field strength at point x due to the red charge. And then we're going to find the electric field strength at point x due to the blue charge, and we're going to add those two vectors together. Okay, so let's start with the electric field created by the red charge, the -1 microcoulomb right here. Now the equation to calculate the electric field strength due to a point charge is kq over r squared. Okay, so we have our k, that's 9 times 10 to the power 9. We have our Q, which is 1 microcoulomb, so that's 1 times 10 to the -6, actually, coulomb, divided by the distance between these 2 points squared, so divide by 1 squared. Now you might wonder, why didn't he put the -1 in here? Well, remember that the charge is -1, but charge is a scalar. So if we end up with a negative value for electric field strength, that doesn't really help us. What's more helpful is to draw in the direction of the electric field at point x due to the red charge. Now, again, to remind you, the direction of the electric field is the direction that a positive charge would feel a force. So hypothetically speaking, if I put a positive charge at point x, which way would it feel a force due to the red charge? Well, the red charge is a negative charge, and so hypothetically speaking, if I put a positive charge here, it would feel a force to the left. The reason I didn't put a negative sign in here is because that negative sign tells me nothing. Whether E is positive or negative, see, again, people get confused by this because charge can be positive or negative, but that doesn't indicate direction. If E is positive or negative, that negative sign now indicates direction. And so the negative sign does nothing for you in terms of calculation other than maybe like confusing you as far as which way E is pointing. I don't need a negative sign to indicate which way E is pointing because I can look at the picture and know that E is pointing to the left. Now, someone out there, by the way, might say, but if you put a negative sign, if I had put a negative sign in front of the 1, then I would get a negative value for E, and E is pointing to the left, and so, that actually helps me. But hypothetically speaking, let's say point X was over here on this side. If X was over here on this side, if I put a positive charge here, that force would be to the right, okay, in the positive X direction. If I had put the -1 in that case, I would end up with a negative value for E, even though the electric field is actually pointing in the positive direction. Okay, so all that to say that I don't bother putting negative or positive sign, or obviously I put in positive signs. I don't bother putting in negative signs into my calculations in this unit because it actually is more likely to confuse me more than anything else. I don't need a sign to tell me which way the direction is supposed to be. I can just look at the picture. Okay, so in any case, I do this calculation, I get 9 times 10 to the 9 times 1 times 10 to the negative 6, divide by 1 squared, and I get 9,000 newtons per coulomb, and the direction is in the negative x direction. Now I find the electric field strength due to the blue charge. I will do that in blue over here. And again, it's the same equation. It's kq over r squared. So I have 9 times 10 to the power 9 times, now I have 2 microcoulomb. So 2 times 10 to the negative 6 divided by the distance squared. And now here you have to be careful. Remember, it's the distance between the point charge and the point in space where you're calculating the electric field. The distance between the blue charge and point X is 2 meters, not 1 meter. Because this is a meter, this distance is also a meter, so I should divide by 2 squared. Okay, so I do 9 times 10 to the power 9 times 2 times 10 to the negative 6, divide by 4, and I get 4,500 newtons per coulomb. Now, what direction is that acting in? Well, let me think. Okay, so I know that blue is positive, so hypothetically speaking, the electric field at point X created by the blue charge would be pointing to the right, because if I put a positive charge there, it would be repelled away from the blue charge, and so that force would be to the right. So the electric field due to the blue charge should also be to the right. Okay, so what is the answer to the question? Well, it's just the vector sum of these two quantities. Okay, so the total electric field at point X would basically be, red E plus blue E. It would be negative 9,000. Here I say negative because here I can tell from the picture that this 9,000 newtons per coulomb is to the left, plus positive 4,500 newtons per coulomb to the right. And so the answer to the question is negative 4,500 newtons per coulomb. That is 4,500 newtons per coulomb to the left. Okay, so the magnitude of the electric field at X is 4,500 newtons per coulomb. The direction is to the left. That is the answer to example 5. Okay, so pause there if you need to look at that some more. This type of problem is a very common type of problem that you'll see on IB questions, where it doesn't necessarily require any calculations, but it requires you to understand the concept and the equation of K Q over R squared for electric field strength. Okay, the IB loves to ask questions like this, especially on multiple choice questions. The question says 2 stationary charges are shown. At which point is the electric field strength the greatest? Okay, so each of these 2 point charges is going to create its own electric field strength. Okay, we're asked either A, B, C, or D, where is the electric field strength, the overall electric field strength going to be the greatest? And so I'll tell you the best way to approach this type of problem. First of all, I'm going to do this in color just to make it easier to see. Okay, I'm going to call this one the red charge, and I'm going to call the other one the blue charge, just so you can visually see what's happening. Okay, so what I'm going to do is I'm going to sketch the direction of the electric field vector for each charge at each of the 4 points individually. Okay, so here's what I mean. Let's start at point A. At point A, if I were to draw in the electric field due to the red charge at point A, I would think, okay, if I put a positive charge here, which way would it feel a force due to the red charge? Well, positive and positive repel, so it would feel a force to the right. Okay, so the electric field at point A, just solely from the red charge, would be to the right. Now, what about at B? Well, it would also be to the right, but it would be bigger in magnitude. Now, how do I know it would be bigger? Well, because the equation for the electric field strength due to a point charge is kq over r squared. Okay, and so distance is a factor in electric field strength. How far you are from the point charge matters. The closer you are to the point charge, the bigger the electric field at that point. Okay, so that's how I know to draw the arrow longer at point B. Now, what about at point C? So again, I think, okay, at point C, if I put a positive charge at point C, keeping in mind there is no positive charge at point C. We talked a lot about that in the last video. You don't actually need a point charge at point C for there to be an electric field there. Okay, but if there was a point charge at point C, it would feel a force repelling it away from the red charge, and that would be, in this case, to the left. Okay, and I don't know that I've done the best job, but just eyeballing this, B and C look to be about the same distance away from the red charge, and so these two arrows should be about the same length. I don't know if I quite did that correctly, but they're roughly the same length. And of course, D, if I put a positive charge at D, it would also feel a force to the left, but because the distance is bigger, the magnitude of that electric field would be smaller. So what I've drawn so far is the electric field strength, okay, due only to the red charges, or red charge, at A, B, C, and D. So now I'm going to do the same thing for the blue charge. And notice the blue charge is negative Q. Okay, so number one, it is a negative charge and not a positive charge. And also it is smaller in magnitude than the red charge, which is 2Q. Okay, so at point A, if I put a positive charge at point A, it would be attracted to the blue charge, and so it would feel a force to the left. Okay, now I'm kind of guessing on the length here. You might say, like, why did you draw them the same length? Because, you know, isn't that charge smaller than the red charge? It is smaller, but also the distance is bigger. And so, you know, maybe those two things kind of compete with each other. I don't really know. I could be wrong about them being the same length. It doesn't matter for this question, as you'll see in a minute. At point B, if I was a positive charge, I would feel a force attracted to the blue charge. And so that would be something like this. Now notice I've drawn this blue arrow shorter than the red arrow. In fact, it's about half the size because point B looks to be between halfway distance between the red charge and the blue charge. And so if the distance is about the same, but the blue charge is half the size, that means the electric field strength would be half as big. At point C, if I was a positive charge at point C, I would feel a force to the right. Notice now this arrow is much, much smaller than this other red arrow though, because I'm really far away from the blue charge, and plus the blue charge is smaller to begin with. Okay, and so D would be something even smaller than that, something like that. Now at point D, I'm really far away from the blue charge, and plus the blue charge is smaller than the red charge. Now, I don't need any numbers to do any calculations for this question. I can see right away what the answer is. The answer to the question is B. B as in boy. And I can see that because at each of the four locations, I basically have two electric fields combining together. But at three of the four options, the electric fields are opposing each other. Whereas at point B, the electric fields are going in the same direction, so they would actually add together. Okay, and so the answer to the question is B. And I said this before, but this is the type of question that the IB loves to ask, especially on multiple choice questions, because it doesn't require any calculations, but it does require you to understand the concepts involved with the electric field strength and how to calculate electric field strength due to a point charge. Okay, so there's no values given here other than the relative sizes of the charge. We're not even given the explicit distances, but we can infer what we need to infer from the picture that's given. Okay, so pause there and make sure you understand how we got that answer. Okay. Okay, so moving on. Okay, so the last thing we're going to talk about in this video is basically visualizing electric field. The electric field near a charge or collection of charges can be visualized using what's called electric field lines. And there are some rules having to do with the electric field lines that you need to add to your notes at this point. rule number one, the direction of the electric field at every point in space is the direction that a positive charge would feel a force. And so as you're drawing these lines at each point in space, you have to also imagine like a little vector at that point in space. So electric field lines point in the direction of the electric field vector at every single point in space. They tend to start at positive charge, and they tend to end at negative charge. I'll show you what that means in just a second. 4. Electric field lines are more dense, where the electric field has a greater magnitude. And by dense, I mean like closer together. Okay, so if you're looking at electric field, like, visually, the closer the electric field lines are to each other, the stronger the field is at that point. In other words, the more lines, the stronger the electric field there. And then step 5, or not step 5, but, rule 5, when you're looking at electric field lines, the lines can never, ever, ever, ever cross. Remember that the way a field works is that every single point in space, you have one specific value of the electric field, like a function. Okay, you can only have one y value for every x value. And that's the same thing with the electric field, or any type of field. You can only have one value at every point in space. So that means if you ever had electric field lines crossing, if you have two vectors crossing, that means at that one point, you have two different values. That's not allowed. That's not physically possible. Okay, so electric field lines can never, ever cross. And I'll show you some examples of electric field lines. Okay, so here we see 6 different charges, and these arrows represent the electric field lines around these charges, and each of these is point charges. Okay, notice that some of them have arrows going away from the charge, and some of them have arrows going towards the charge. Keeping in mind that the direction of the electric field is the direction that a positive charge would feel a force, and that on the last slide it said in the notes that the field tends to point away from positive charge and towards negative charge. With that in mind, you should be able to figure out which of these answer choices are positive charges and which of them are negative charges. Okay, so the first question here says, which field is that of the largest negative charge? Well, negative charge, electric field tends to go towards negative charge. And so, B has a negative charge, D has a negative charge, and C also has a negative charge. If we want the largest negative charge, remember the way we indicate the strength of the electric field is by density. How many lines do we see, or how many arrows do we see in the same amount of space? And you should hopefully be able to realize that D has the greatest density of electric field lines, and those electric field vectors are going towards the negative charge, and so the answer for A would be D. Okay, that field is showing the largest negative charge. Okay, the largest positive charge would be A, for the same reason. Positive charge, if you're thinking of a positive charge, the electric field goes away from positive charge. And then the smallest negative charge would be C. Okay, it's negative for reasons we talked about before, but it's the smallest electric field because it's got the lowest density of field lines. And then the smallest positive charge would be E. Okay, so again, the larger the charge, the more concentrated the electric field. Okay, and I wanted to show you really quickly just a quick simulation, just so you can visually see the electric field around a positive point charge. Notice that at every point in space there is an electric field already, but as I move this positive charge around, it kind of distorts the electric field that's already there. So if I just have this positive charge out there in space, you can see the electric field points away from that positive charge, but it gets darker, meaning in this simulation it gets weaker the farther away you go. And if I put a negative charge out there in space, you can see that also distorts the electric field in the area. Okay, here you can see the electric field vectors tend to point towards the negative charge. and I can make some very complicated distributions of charge, as you can see. If I add in a bunch of charge, you see the electric field start to kind of curve in really weird and strange ways. Okay, but those electric field lines can never cross each other. Okay, so for the most part, that is it for electric field. We just have a little more to clean up in the next video. But a lot of the problems that you'll see, both conceptually and calculation-wise, have to do with either the definition of the electric field or situations involving the electric field due to a point charge, either calculation-based or conceptual like the one that we just did. Okay, that's a very common type of conceptual question to see. And we'll do some more questions like that, I think, during the next class. As always, please let me know if you have any questions, and I'll see you guys in the next video.